Okay, so we're going to cover a new topic now. So everything we've considered so far has been in discrete time, okay, where the time horizon's been infinite or finite. We've always considered a discrete time problem for our Markov decision processes and dynamic programs. Okay, so now what we're going to do is start to move on to a continuous time framework. Okay, so I'm going to do it first for the slightly easier case of dynamic programming, and then we'll work towards the sort of diffusion analog of Markov decision processes. Okay, so we're going to want to end up doing optimal control over diffusion processes. Okay, but so let's start with this deterministic dynamic programming framework. Okay, and then within this we'll cover a specific example called linear quadratic regularization, which is one of the most common control frameworks. It doesn't have to be continuous time, but it fits quite nicely within that. And it's commonly applied in engineering settings. Okay, right. But anyway, to start with, let's go through all the definitions and our analog of the Bellman equation for continuous time problems, which we're going to call the Hamilton-Jacobi-Bellman equation. Okay, I'll go through some of the arguments as to why that is the correct equation to consider, and then I'll give a proof of why it is actually the optimality condition for this type of problem. Okay, right. So here we go. Continuous time dynamic programming. Okay, so discrete time dynamic programming was given in the first lecture. Okay, we're now going to consider its continuous analog. Okay, so time now is going to be continuous. Okay, so it's going to range over all the positive real numbers. Okay. And again, the state x of t is going to belong to some set script x, okay? And usually we'll imagine x belonging to some sort of vector space, like the reals to the power of n or something like this, okay? And then, again, there's some actions, a of t, which belong to some action set, okay? And we can allow ourselves to be a little bit more abstract about what the sets of actions are. We don't need to assume they belong to some real set of real numbers or anything like this. Okay, now we need an idea of the evolution of this system, just as before, where we have the Plant equation. Okay, so as before, the Plant equation was just a deterministic function where we take our current state, our current action we've chosen, and then this determines what the next state is. It's the same idea now, but we're going to use a differential equation to give that. Okay, so the Plant equation is given by a function, f, which takes a time, a state, and an action as its input, and then outputs something in the sets of states we can take. Okay, actually it's going to output like a change in x. Okay, and then so the states evolve according to a differential equation. Okay, so specifically the change in x of t, okay, the state, is given by this function f of t, x of t, a of t. Okay, and this is the Plant equation in this case. All right. Now, again, like before, we need an idea of a policy. Okay, so a policy chooses an action pi of t at each time t. Okay. The instantaneous reward for taking an action A in state x at time t is then going to be given by some reward function, r of t of a of x. Okay, so the reward for action A in state x at time t is given by this r function. And we're also going to assume a finite time horizon problem, and thus when we finish time at the end at capital T, there's going to be some reward for that, r of capital T of x. Okay, so that's the reward for the termination state where you end up. Okay, now we can give the definition of the dynamic program in this setting. Okay, so given some initial state x of 0, a dynamic program in continuous time is the following optimization problem. Okay, so we're looking, so here I've done it for costs, okay, so just to mention, so I'll be using little r for rewards and little c for costs, okay, and I can change between minimization and maximization depending on whether I'm referring to a cost minimization or reward maximization. Okay, so that's just the same as before. Okay, so I'm phrasing this dynamic program as a cost minimization problem. Okay, the same situation will occur as before for the maximization of rewards as well. Okay, so given initial state x0, a dynamic program is an optimization problem where the optimal value function, L of x0, is equal to the minimum, okay, of the costs given the vector of actions that I've chosen. Okay, so given the sequence of actions that I've chosen, which I've used bold A here to denote, we're looking to minimize the integral of all the costs. Okay, so rather than summing up all the costs for each action taken, we're now integrating the costs for each action taken. Or if it's a maximization, we're integrating the rewards for each action taken. Okay, and then finally we add on, in addition, the termination cost. Okay, now I've also applied a discount factor here, all right, which in a financial problem would correspond to kind of our rate of interest, or the way that money devalues itself over time. Okay, so we don't need to include this. We could absorb it into the cost here, but given that we're going to be looking at financial problems, I think it helps to include that from the start. Okay, so we're going to minimize the integral of all the costs subject to our plant equation. Okay, so we have x of t changes as a function according to the following function in our plant equation. Okay, and a bit like before, I'm going to let c of tau of a be the costs from time tau onwards for taking a set of actions. Okay, and then I'm going to let L of tau of x of tau be the optimal value function from time tau onwards. Okay, so if you're in state x of t at time tau, or x of tau at time tau, then this gives the best you can do from that point until the end of time. Okay. Okay. So when we consider a minimization problem, we minimize the loss given the costs incurred is replaced with a when it's replaced with a maximization problem, we maximize the winnings, the rewards, so the functions L, C, and little c are going to be replaced by W, capital R, and little r. Okay, I've been using V and W interchangeably here, so we can either have L, C, and little c, and W, R, and little r. Okay, and I probably need to decide on my notation whether I'm going to use L's and C's. So this is part of the general evolution of the course over time. Okay. Okay. So now we've written down what a dynamic program is in continuous time. Essentially what we've done is we have the same sort of evolution as before, as a differential equation. And we have the same sort of summing form as before, but now it's an integral. Okay? So now we need to write down what the analogue is of the Bellman equation. Okay? So for continuous time problems, the Bellman equation is called the Hamilton-Jacobi-Bellman equation. Okay? And I guess sort of the names Hamilton and Jacobi get appended to this because of their sort of work in problems to do with energy and physics. And so there's a similar sort of theory that these guys have contributed to and then is applicable to the kind of dynamic programming setting. Okay? Anyway, so for a continuous time dynamic program, okay, as given above, the following equation is called the Hamilton-Jacobi-Bellman equation, and this is a continuous analogue of the Bellman equation. Okay? Now, it's going to have a similar sort of structure to before. Okay? You're basically looking to minimize the instantaneous costs, okay? And then some function that then accounts for what's going to happen next relative to where you are, L of t of x, okay? So this we can think of in a very similar way to the way we looked at the kind of future costs, okay? And notice we've actually set this equal to 0, okay? So normally we would have had L of t of x is equal to this minimization over here. And in fact, what you'll see in a minute is actually we've kind of absorbed it into this term over here and made it into a derivative. Okay, we'll see that in a second why that is. All right. Okay, so we have that the minimization of the instantaneous cost plus the value from there on out deducted from the value currently is equal to 0. Okay, all right. So now what I want to do is explain to you sort of why this is the HJB equation. Okay, so where did this come from? It's a bit complicated expression. We've got partial derivatives of the value function with respect to t, partial derivatives with respect to x. So we've got various things going on. Okay, so we need to kind of think about why that's happening. Okay, what I'm going to do is essentially look at the kind of terms that we had before, but try to discretize them so we can put it back in the discrete time framework. Look at what the Bellman equation was for the discrete time framework and show that as we let the intervals of time get smaller and smaller and smaller, okay, that our old Bellman equation will become this Hamilton-Jacobi-Bellman equation. Okay, so we need to essentially set everything that we're considering in continuous time into a discrete time framework. Okay, and that's going to involve lots of sort of Taylor expansions. Okay, and replacing our integrals by summations. Okay, so let's do that. All right, so we're looking for, over the next few bits, is a heuristic derivation of the HJB equation. Okay, so the first part that we have is to argue that for delta greater than or equal to 0 and small, sorry, pardon me, x approximately at least satisfies the following recursion. Okay, so this should be a good approximation for the Plant equation over here. Okay, so it should be a good approximation for this. Okay, and why is that? Well, so that's not too hard. We know that dx of t dt is equal to f of t of x of t of a of t. Okay, and we know that dx of t dt is equal to the limit as delta goes to 0, so just from the definition of the derivative of x of t plus delta minus x of t divided by delta. Okay, so if we forget about the limit in here and just work with one of these terms, which is going to approximate this derivative, so we're going to have that x of t plus delta minus x of t divided by delta is approximately equal to f of t, x of t plus a of t. Okay, so if we take something that satisfies this recursion, it's going to approximately do the same thing as this differential equation over here. All right? Okay, so I'm being a little bit hand-wavy and heuristic, and I'm going to keep being a bit hand-wavy and heuristic. Okay, but it's just to get the main ideas across. Okay? Okay, now argue heuristically that the following is a good approximation for the objective of a continuous time dynamic program. Okay, so let's just remember that we have the cost of a sequence of actions is the integral from 0 to t e to the minus alpha of t, c of t, x of t, a of t dt plus the termination cost. All right, well, so why is that? Well, there are a few things we can say. Firstly, that e to the minus alpha of t, okay, is equal to the limit as delta goes to 0 of 1 minus alpha delta t over delta. Okay. All right. So in some sense, the definition of the exponential is this limit over here. All right. So just in the same way as up here, I've replaced this limit with the actual delta term. I could do the same for this. Okay. So I could do it for the e to the minus alpha t, which is kind of the discount factor in that problem there. Okay. Further, we know that the integral from 0 to t of some function let's just say it's a function in t is equal to, assuming suitable continuity properties, is equal to the sum, okay, of over different times 0 up to delta times t minus 1, okay, then delta times g of t. Okay, so the idea there is our usual idea from integration, that we've got some function g, and we've got times t, and the area under this curve can be approximated by lots of little intervals, lots of little rectangles, okay, that just fit below, and the distance between each the width of each rectangle is delta. Okay, so this delta times g of t is essentially the area in this rectangle here. Okay, and we just sum up all those rectangles. So that's our usual kind of Riemann integral argument. Okay, for the existence of the integral. Okay. Right, so if we put those two things together, all right, what we're going to end up with is that the integral from 0 to capital T e to the minus alpha t c of t of x of t a of t dt plus e to the minus alpha of t c of t x of t is approximately, well, we'll replace the integral by this sum, the sum from t equals 0 to delta times t minus 1 of the term inside here times delta, so delta times e to the minus alpha t, which I'm going to replace with this, 1 minus alpha delta t divided by delta, times the value of c of t of x of t of a of t, okay, and that's replaced all of the integral parts, and then finally we've got the cost for the termination state here. Okay, so I can replace the exponential with this delta term. Sorry, that should be a capital T. Okay, and then the termination cost. Okay, so that's sort of why that is a good approximation of the cost function. So that's our original cost function from the continuous time problem, and here's the kind of discrete analog of that. Okay, so now instead of integrating up costs, we're summing up costs just like we did before. Okay, okay. So now show that the Bellman equation for the discrete time program with objective 5 and plant equation 4. Okay, so here that's 4 and that's 5. Okay, is the following. Okay, so we just do the same thing that we did before. We say that the instantaneous cost, the cost, optimal cost, is the minimum over the sets of actions that we can take of the instantaneous cost. Okay, so in our case, the instantaneous cost, all right, ignoring the kind of discount factor here, is delta times c of t, a of t of a. All right, so that's the instantaneous cost at time t of taking action x. All right, and then we're going to move on one step further. Okay, apply 1 unit of our discount factor. Okay, because the value of the money is devalued a little bit each time we go forward, and in this specific case, money is devalued by a factor 1 minus alpha to the delta, okay, or to the times delta, okay, and then we look at the value from that point onwards, okay, L of t plus delta, because we've moved delta units of time onwards, okay, and we evaluate that at the state we've just ended up at. So this is kind of our x hat. According to this equation, the next state I end up with is equal to x of t plus delta f of x. Okay, so x of t plus delta f of t x of a. All right, so it's the same idea as before. We've got the instantaneous cost plus the future costs, and we've applied our discount. Okay, so we've seen this already. Okay, So this is just a normal Bellman equation. And we've got an objective, which is to minimize this sum of costs. We've got a plant equation of this form. Okay, so that's just our normal AHJB equation. Bellman equation as previous. Okay, right. Now argue by letting delta approach 0, the above Bellman equation becomes the following. Okay, so now we just need to kind of collect together some of the terms. I'll just zoom out a little bit. Okay, so let's just grab this expression. Okay, and bring it down here. Shrink it a little bit so we've got a bit more space. Okay, so let's rearrange this guy. So what I can do is I can bring, like I mentioned before, bring this L of x of t over to this side of the expression. So this implies, let's zoom in a little bit more. Okay, that 0 is equal to the minimization over the sets of actions I can take, all right, of delta c of t x of a plus one lot of this guy, okay, L of t plus delta x of t plus delta f of t x of t of a minus, take this over to the other side, minus L of t of x, alright, and then what we've got left over is this minus alpha delta. Alright. Okay, now notice I've got a lot of multiplied by deltas here, so what I can do is divide by delta. Okay, so what I'm going to do is if I divide by delta, I'll end up cancelling that guy out, and I'll end up dividing this guy by delta. Alright, so now I've got something that looks a little bit similar to what's up here. I've managed to pick up something that looks similar to this alpha L of t of x here, alright, and I've managed to pick up something that looks like this cost here, and then I've got a term in the middle which looks a bit like a kind of derivative term. Okay, so now let's think what happens to this guy. Alright, so we're essentially taking a derivative of L of t of x. Well, we've moved on a bit in the time component by delta. Okay, that suggests that we're going to take a partial derivative of this guy with respect to time, and we've moved the state component on a bit, delta f of t x of t of a. All right, so we've moved the state on a little bit as well. All right, so in other words, what we're going to end up with is a partial derivative of this function in time. We've moved on delta units, okay, and a partial derivative in the state where we've moved on f of t of x of t a units for every 1 unit of delta. All right, so what we're going to pick up is a time partial derivative and a state partial derivative. Okay, so in particular what's going to happen is I let delta go to 0. All right, is, well, this has got nothing to do with delta, so this is going to stay the same. This is going to converge to a partial derivative in time. This guy, where we, for every 1 meter move forward in time, I'm differentiating with respect to 1 unit in delta. Okay, and a partial derivative in space. Okay, where I take a partial derivative with respect to x of L t of x, where for every 1 minute I move along in space, I move f of t of x of t units in space. So I need to multiply this by f of t x of t of a. Right? And then finally, we've got a term with delta here. Well, we're not dividing by anything by delta. So as I let delta go to 0, this is just going to converge to L of t. And this term is going to vanish towards 0 as well, and we're just going to be left with x of t. Okay. So this is just going to converge towards that. Right? In other words, you can check that this is exactly this up here, which was our Hamilton-Jacobi-Bellman equation. All right? So by looking at this as a discrete time dynamic program, and then letting the sort of spaces between times get smaller and smaller, we're going to converge towards this Hamilton-Jacobi-Bellman equation. Okay, so that's why the Hamilton-Jacobi-Bellman equation is the natural analogue of the Bellman equation for a continuous time dynamic program. Okay, now that's kind of a bit hand-wavy and heuristic, but you can actually prove that if you solve for this finite time horizon problem, that if you solve the HJB equation, then you've actually solved the optimization problem. Okay, so let's show that. It's actually not too bad. Okay, so let's say that we found a policy, pi, that has some value function c of t of x of pi that satisfies the HJB equation for all t and x. Then we can show that that policy is indeed the optimal policy. Okay? And the hint for showing that this is the case is to consider the following function, e to the minus alpha t c of t x tilde of t of the policy pi, where pi tilde are the states visited by some other policy, not the optimal policy. Okay? Right. So let's have a look at that guy. All right. So what we can do to answer this question, to show that solving the HJB equation actually gives us an optimal policy, is to essentially differentiate this guy. Okay, so we're going to look at e to the minus alpha t c of t x tilde of t of our policy pi. All right. Notice that if I go from time 0 to time capital T, I'm actually interchanging between the cost function of that policy, the cost function of the policy pi at time 0 to the termination state of the policy x tilde. Okay, so what I'm saying there is notice that at time this, if I look at this function, it starts at time t equals 0 at just the cost of being at the initial state x0 and following policy pi. And it terminates at the termination cost that you get from capital T of pi. Okay? And what I'm going to show here is you can pick up the costs in between those states for the policy given by pi tilde as well. Okay? Alright, let's see that. So I can differentiate this guy. Alright, so I'm going to differentiate the first term, which is going to give me e to the minus alpha of t. Okay, and then I'm going to pick up a minus alpha here, which will multiply by this minus sign, give me an alpha, t x tilde t pi. Okay, so I've just differentiated the first of these two terms. Then I'm going to differentiate this term. Okay, so I'm going to keep the e to the minus alpha t and differentiate this guy. Okay, so if I differentiate this with respect to time, I need to apply the chain rule to this. I've got two components which depend on time. So I have to differentiate the space component and the time component. Okay? So specifically, what I'm going to pick up here is the partial derivative of this guy with respect to time. Okay? And I need to differentiate this part, seeing as it evolves with time as well. All right. Here I'll get the partial derivative of the x component. Apologies for my bad writing. Okay, so we've got, I'll write that below. Just give me a second. I'll get the partial derivative of this guy with respect to space, okay, of c of t of x tilde of t of pi. Okay, but notice for per unit time I move here, I don't move 1 unit here, I move the derivative of this with respect to time units. So times the derivative of x tilde of t dt. Alright? So now I've just done the differentiation, standard differentiation rules. Okay? And what I can notice here is that I'm going to have e to the minus alpha t. And what I'm going to do is I'm going to add on and take away the cost of following policy pi. Okay? I'm going to end up with minus the cost of x tilde of t following policy tilde. And I'm going to look at each of these terms and compare it with the HJB equation. So I'm going to have minus alpha c of t x tilde t of pi. Okay? And then I'm going to have here, alright, I'm going to have f of t, because notice this evolves according to time according to the Planck equation, so x of t tilde pi of tilde of t, okay, times the partial derivative, delta x c of t x tilde of t of pi, okay, and then I'm going to be left with this time derivative as well, okay, so plus delta t, not delta t, the partial derivative with respect to t of c of t x tilde of t of pi. Okay? Alright, now let's look at this term here in these curly brackets. Notice that that is exactly the curly bracketed term here, alright, for the optimal value function. Okay? So we've said that it solves this equation with c of t of pi in the place of L. Okay? But notice we're not guaranteed that the choice I'm making here, pi tilde of t, or pi tilde of t here, is the optimal choice. Okay? So instead of minimizing over the actions, I've written the same expression down, but with pi tilde of t. Okay? So in other words, in this expression here, I've got something that isn't equal to 0. It's not minimizing, apologies. It's not minimizing this, okay? So it must be bigger than 0. So this term here must be bigger than 0 in this brackets, okay? In other words, minus this term must be less than 0. So we've got something that's less than e to the minus alpha of t c of t x tilde of pi tilde of t. Okay? So now we notice that this derivative here is less than the instantaneous cost that I'm getting from the policy pi tilde. In other words, the cost function associated with policy pi, which solves the HJB equation, seems to have a lower instantaneous cost than that from following policy pi tilde. Okay, so what we can do here is we can integrate this out. Okay, so now let's integrate this, both sides of this expression, from time 0 to time capital T. Okay, so integrating both sides gives, so on the left hand side I'm going to get the integral from 0 to capital T, e to the minus, alpha t, c of t x tilde of t pi tilde of t dt, and that's going to be less than, okay, notice I'm going to pick up from here something that starts at the cost function x0 of pi and ends up at ct of pi, okay, so what I'm going to end up with here, or e to the minus alpha capital T of that, so I'm going to end up from integrating this side, okay, is c of x of 0 of pi minus the termination cost at time capital T under policy pi tilde. Okay? So notice, if I just move this guy over here to this side, then I've got the cost of policy pi tilde compared to the cost of the policy pi. Okay? So that implies that the cost of x0 pi is less than the cost of x0 pi tilde. Okay? So in other words, for any policy that I choose pi tilde, my policy that solves the HJB equation, the Hamilton-Jacobi-Bellman equation, has a lower cost. Therefore, pi is optimal. And that's it. Okay? So next we'll cover kind of the LQR theory, which is a specific example of these kind of continuous time control problems.